So welcome to session number 5 of the module 1 stress and strain, in which we are discussing about how the material behaves when the load is applied. So in the last session we have seen for different cross sections of the bar when the load is applied, how the stresses will be developed and how to calculate stresses in the material at various cross sections, and also to how to calculate the elongation or the shortening of the bar when the tensile load or compressive loads are applied on the material. So here we have one more problem wherein the loads are applied at different points of the bar, and the bar is having varying cross sections for different lengths, as you can see here. So here we have a bar, circular bar. It's a circular bar because diameter is given at all the cross sections, and the diameter is varying with different lengths of the bar. This is the configuration free body diagram of the bar, and you can see the load is applied at different points and in different directions. So we have tensile loads as well as compressive loads at different points. So in this case we have to be very careful while analyzing the portions of the bar. So here we divide the bar into 3 portions, as you can see here, 1, 2 and 3, because diameter is varying for different lengths. Though the metal is same, but we divide the portions, we divide the bar into 3 portions based on the cross-sectional diameter. And also the load is applied, different loads are applied at different points on the bar. So you should be careful here, and Young's modulus is given, and the remaining dimensions, diameter, length, load, etc. is given in the diagram here. So what you have to find out is, we should determine the overall change in length of the bar. So we should find out what happens to the length of this bar, whether it decreases or whether it increases, because as you can see here, loads are in different directions. We have tensile load as well as compressive loads. So we don't know, until we calculate, we don't know whether the length of this bar or rod will decrease or will it increase. So we will see that. So in this kind of problem, so what we do is we draw the free body diagram of this bar, wherein we draw each portion or each section separately. For example, we take bar portion 1 of this portion 1 of this bar, and we analyze the forces on this, and once we understand the forces on this, we can calculate the elongation of this portion of the bar. Similarly, we analyze or we try to simplify and study what is the load applied on this portion of the bar, because at the 2 ends load is applied, and then once you know the load applied on this portion of the bar, we can easily calculate the elongation or shortening of the bar. Similarly, we do the same thing for this portion of the bar. So in this case, in this type of problems, first we divide the bar into 3 portions or any number of portions based on the cross-sectional diameters. So you can see here in this free body diagram, this is portion 1, and this is portion number 2, this is portion number 3. So in portion 1, we analyze the forces acting on portion 1. So we take this portion 1 and we just follow the left hand side. You take the left hand side of the portion, that is at this point, and you see what is the load applied on the left hand side of this bar here. So on the left hand side of the bar, it is 30,000 or 30 kilonewton. So for this portion, left hand side, the load applied is 30 kilonewton. So for equilibrium condition, this load will be will be opposed, or to keep the portion in equilibrium, there will be reactional force in the opposite direction. Equal and opposite reaction will be there in this right side of the portion. So whatever load is there on the left side of this portion, the same load will be there on the right side of the portion, which is equal and opposite direction, to maintain this portion in equilibrium. So this is portion number 1, and on this portion you can see compressive load is applied now of 30 kN. So now we have the portion of the bar with only compressive load of 30 kN. Coming to second portion here, the second portion again you take this portion here and you take the left side of this portion. So left side of this portion is this one. So at this left side you just analyze, or you just observe what forces are acting on the left side portion of this bar. So on this portion of the bar you take the left side. So on this left side you have two loads acting in the same direction, that is towards this portion. So this is the second portion. You just forget the first and third portion. You just imagine, consider only the second portion here, and on the second portion you take the left side of this second portion. So on the left side of the second portion, that is here, you have only two forces acting, that is 30 kN and 20 kN, and both are acting in the same direction, it is towards the second portion. So 30 plus 20, that is 50 kN. So now in the second portion, on the left hand side, 50 kN is acting on this second portion. So you can see here, second portion is here, left hand side we have two forces, 30 kN and 20 kN. So add those two, so it will be equal to 50 kN. So in the second portion, left hand side, 50 kN is acting. So if you want to maintain this, if the second portion has to be in equilibrium, there should be equal and opposite reaction on the right hand side. So 50 kN on the left hand side, therefore right hand side also will be 50 kN. So this is the second portion, and in second portion the load is compressive and it is equal to 50 kN. And in the first portion the load is compressive and it is 30 kN. Similarly you analyze for third portion now, in the same case. So third case again, you come to third portion here, you take third portion and you take the left side of the third portion. So at this point, at the left hand side of the left hand side, you just observe what forces are acting. So here we have one force, that is 3400 Newton, and we have 20 kN and 30 kN. So 30 plus 20, it is 50 kN, and this at this left hand side, this load at this point is acting in the opposite direction, 34,000 Newton. So 50,000 minus 34,000 Newton, it will be equal to 16,000 Newton. So either you can take left hand side and add all the forces, or since one more force is acting on the right hand side, you can take third portion and you can take only this load, and the same load will be acting on the other side. So if you take this third portion, that's the right hand side portion, on the right hand side this is load is applied, so you can equate it to on the left hand side also it will be same, or else you just take the left hand side of the portion, left hand side of this third portion. On the left hand side at this point, 3004 Newton is applied on the left direction, and 50,000, that is 20 plus 30 Newton, that is 20,000 plus 30,000 Newton is applied on the right hand side at the left hand side of the portion. So if you minus 50,000 right hand side, 34,000 left hand side, so if you take the resultant of that, it will be total will be net load acting on the left hand side of the portion will be 16,000 Newton, and since 50,000 is greater than 34,000, so the load will be acting towards the third portion. So load will be, this load 16,000 Newton will be acting right side of the the third portion here. So similarly on the right hand side, to maintain this equilibrium, the same 16,000 Newton will be acting on the right hand side. So either you can take at the right end of the third portion, it is right end. So at the right end it is 16,000. So to maintain equilibrium, the same 16,000 will be acting here. So either you can calculate from the left hand side, or you can take the right hand side load and equate it to the left hand side of the third portion for equilibrium. So once we know the loads acting on three portions, we can easily calculate the elongation or shortening of the bar or the change in length. So you take separately this portion number 1, and you calculate the change in length or elongation or the shortening. So you can easily say that in portion 1, since the load is compressive load, it will shorten, so length will decrease. So the change in length or shortening of this portion, for that formula yesterday in the last session we have seen that change in length is nothing but PL by AE. So this formula holds good for all the portions. So you can see this is for portion 1, this is for portion 2, this is for portion 3. So for each portion the formula remains same, change in length, change in length, change in length of the first portion, second portion and third portion. The formula also remains same. So in the first portion, PL by AE. So P is the load applied. So load, it is 30 kilonewton. Length is given in the problem. So length of this portion is 100 mm. And area you have to calculate. It is a circle here, circular cross section. So area of this circular cross section will be pi by 4 d square. D is given here, diameter is given, and PL by AE, Young's modulus. So material is same. So all the portions, it is the same material of the bar. So Young's modulus is given as 1 lakh Newton per millimeter square, or we can take it as 100,000 megapascal. So it is 1000 here. So you can make it as 100 kilo into megapascal. So kilo is 10 power of 3, mega is 10 power of 6. So you can say it as 100 GPa, whatever it is. So you keep the values here. So come to the formula here. So for each portion you apply the load. Load is So for first portion it is 30 kilonewton. Second portion it is 50 kilonewton. Third portion it is 16 kilonewton. Length of first portion is given. Second portion is given. Third portion is given. Area of first portion you calculate because diameter is given. Okay, calculate all the areas for first, second and third position, and Young's modulus will be same for all the portions. So you calculate each one separately, that is change in length you calculate, and you can see here that all the portions are compressive. So this is compressive load is there, second portion also compressive load, third portion also compressive load. So obviously what happens, the length of the bar will shorten, will decrease. So it is called a shortening of the bar. So each portion you calculate. So this is all negative here. So all are shortening here, and you add all the three things. So total decrease in length. So length will decrease. So the bar length will decrease. The total decrease in length is nothing but you add all this shortening of the bar. So 0.09, 0.45, this one, and you will get the total decrease in length. So this is it is called a shortening of the bar. So bar will shorten, length will decrease. And remember here all the units you have to keep it in millimeters or meters. So load anyway keep it in newtons. It is given in, if it is given in kilonewton, you convert it into newton, that is kilo is 10 power of 3, you take it in newton. Length is given in millimeters. Area also you take it in millimeter square. So area will be in millimeter square, length will be in millimeters, and this Young's modulus will be in Newton per millimeter square. This should be Newton per millimeter square. So all the lengths are in millimeters only now. So that uniformity in units you have to maintain. So after this kind of problems you have to analyze. So whenever the load is varying on each points of the portions of the bar, you divide the bar into separate portions and you analyze the loads on them, and then you apply the formula separately for each portion. And then if the length increases you add, or if the length decreases you add again, and the length will decrease here. So suppose say that second portion is the load may be tensile load. So in the second portion the load is tensile, first portion it is compressive, third portion it is compressive. So what will happen here? So you take this as negative, it is compressive negative, the length is decreasing, tensile positive, length is increasing. Then it is third portion is compressive, it is negative, length is decreasing. So we add all the things. So what happens, you get ultimately you may get, if it is negative you may say that the length is decreasing. If this is positive, if any one is positive more than the other two, then if you sum all the deformations, all the elongations or shortening, change in length, then if it is positive then the length will increase. So here you have to write total increase in length if the length is increased. So here we have one more derivation, a small derivation, wherein you will be calculating elongation of a bar, which is where the cross section is increasing or decreasing linearly. So here you can see, so this kind of bar is called as tapering bar, whereas in the previous case this is called a stepped bar. So because step is there, diameter is changing, we call this as stepped bar. If the diameter is same over the length of the bar, we call it as straight bars. So we have straight bar, then this is called as stepped bar, and we have one more kind of bar called as tapering bar. So tapering means the diameter or thickness of the bar will decrease uniformly through the length. And this bar is, the cross section is circular cross section. So this is a circular cross section bar, and the diameter decreases from D2 to D1 over the length L. So in this case, how to calculate the elongation, or how to calculate the shortening of the bar when the load is applied on this bar. So here in this case, the load applied is tensile load. So load applied is tensile load on this bar, so on this tapering bar. And when the load applied is tensile load, it will be, the bar will elongate. The change in length will be positive, it will elongate. If you apply compressive load, then change in length will be negative. So here we will derive for tensile load only, and then we will apply the same thing for compressive load also. So here we have a tapered bar. Diameter here at one end is D1, diameter at the other end is D2. D2 is greater than D1, and P is the tensile load applied, that is axial load applied on this bar, tapered bar. So now we have to analyze this, and we have to calculate what is the stress in this, and what is the strain, and what will be the elongation of the bar. So here we take a small element, for mathematically we take a small element with diameter D, and the length of this element is taken as dx. So this is dx at a distance of x, and then we calculate the stresses and all those things in this element, and we integrate this over the length, so that we calculate the elongation of this element, and we integrate that elongation over the length of this bar. So here we have to input, or we have to use the calculus differentiation and integration to find out the elongation of this bar. So initially we start up with taking a small element at which is having a diameter D, and the length of this element you take it as dx, and this is at a distance of x from left hand side from A. And then what happens, you have to use mathematical theorems here. So using principle of similar triangles, so what happens here is this diameter of this element will be equal to, it will be d1 plus, so it will be more than this d1, so we get d1 plus, and it will be d2 minus, that is d2 minus d1 by L over the length L into x at this distance x. d2 minus d1, that will give the difference of these two diameters over the length L, and into x. X is because you have taken this element d having diameter d at a distance of x from left hand side. So to simplify this term, we take this d2 minus d1 by L as k, small k. It is just to simplify, okay. Just keep in mind that k is nothing but a difference in diameters over length L. So this equation becomes d1 plus k into x. And now we take the cross-sectional area of the bar at x. Okay, so we will take the cross-sectional area at this cross-section, that is, we have taken at a distance of x, and the diameter of this is d, and d just now we have seen what is d. So d is equal to d1 plus kx. So now you have to calculate the area at this cross section at a distance of x. So what will happen? Area will be again pi by 4 d square. So area at x, area at this cross section will be pi by 4 d square. So pi by 4 is there, d means this d1 plus kx. So d is d1 plus kx. So pi by 4 d square. And once you know the area of the cross section, and once you know that load is acting P, we can easily calculate the stress at x. So stress is sigma, x is the that is at cross section which is at a distance of x from A. So it is stress at x is nothing but load, that is P is acting, and area at the point x. So this P already you know, keep it as it is. A is nothing but just now we saw here pi by 4 d1 plus kx square. Put that, you will get this area. Then change in length over dx is nothing but delta dx here. So here the change in length of this element, will be dx here. So we take the change in length of the element as stress, that is PL by AE. So P by A is nothing but the stress here at x, and length of the element is dx. Length of this element is dx. So we will integrate this over the length afterwards. So that's why we have taken the length dx here, which is a differentiation of this x. So length is now, length of the element will be dx. P by A is nothing but just now we saw this on the element sigma x, and E is the Young's modulus. So sigma x is nothing but it is this much, 4p you substitute here, and dx keep it as it is, and E also as it is. So the elongation, change in length, that formula we are using it in this case PL by AE. The same formula we will use it here, PL by AE. The elongation of this or change in length of this element will be PL by AE. So P by A is nothing but sigma. So L is nothing but dx. L will be dx and E as it is. The fluid value of sigma x here. So you will get this term here. And now this is the change in length of this element of length dx. So once we know the change in length of this element dx, if you integrate that from 0 to L over the length, we can find out the change in length of this bar, total bar. So integration of this, therefore total change in length or or elongation of this bar delta L will be equal to integration of this term from 0 to L, because I want the change in length over the full length of the bar. Okay, so here you have taken only the element dx, length dx. If you integrate that, you will get over the length L. So integrate that term, so and rearrange, you will get the value of you will get this term here, and k is d1, because k is so much, you just put the value of k here, it's a constant, and you will get this term here. So you can see here the elongation of the bar, tapering bar, will be same as PL by AE. So PL A. So what is A? A is pi by 4 d square. So since we have d1 and d2, since the diameters are 2, so we take it as pi d1 into d2, and E as it is. So this equation is similar to this equation, change in length for straight bar. The only difference is area in the straight bar will be pi by 4 d square, whereas for tapering bar it will be pi by 4 d1 into d2, because we have two diameters for tapering bar. So you have to remember this equation. So whenever the problem is asked for tapering bar elongation, you calculate using this. So it is P as it is, load is there, Young's modulus is there, length of that tapering bar will be given, diameter one end and second d2 will be given, substitute the values, and that will give the change in length of the total tapered bar. So you have one small problem here. A bar uniformly tapers, so it is a tapering bar from diameter 20 to 10 mm. So from diameter 20 mm it tapers, so diameter decreases from 20 mm to 10 mm, and the length of the bar is given 300 mm. And what is the load applied? Load applied is compressive load, 7.5 kilonewton. Then Young's modulus is given. So you calculate the maximum and minimum axial stress in the bar and total change in length of the bar. So here we have to calculate, you can say the stress, it depends, I told you it depends on the cross-sectional area. So since the tapering bar has two cross sections with different diameters, so area also will be changing. So at one end it will be maximum, at other end it will be minimum. So that we will see now. And also you have to calculate the change in length of the bar. So just now we derived the equation. So PL by AE, 4PL by pi E d1 d2. So this is the equation for change in length. Okay. So first we'll calculate the maximum and minimum stresses in the bar. So maximum stress in the bar will occur at the end where the diameter is smaller, because area will be smaller. So we know it is stress is P by A. So if area is smaller, then the stress will increase, it will be maximum. So when the area increases, the stress will decrease. So here you can see, so what we can do is first we will calculate the areas at cross section, at small cross section and at bigger cross section. So if you calculate area at D1, so you take D1 as smaller diameter, D2 as bigger diameter, length is given, Young's modulus is given, and load is given. So you calculate the areas at D1, area at D1. So area at D1 will be pi by 4 d square. So D is 10 millimeter. So D1 is 10 millimeter. So this is the area at smaller diameter. Similarly, area at bigger diameter is 314. So pi by 4 d square. So D is 20 mm. So here in this problem, this D1 is 10 mm and D2 is 20 mm. So you calculate the area at D1 and you calculate the area at D2. So it is circular, so it is pi by 4 d square, pi by 4 d square. So accordingly you put the values, you will get the area. So once you know the area, you can calculate the stresses at two cross sections. So here you have, so as I told you that when the diameter is smaller or area is smaller, stress will be maximum. When diameter is higher or more, that area will be higher, and when the area is more, stress will be less. So from that understanding, the stress will be it is a compressive stress because compressive load is there, and it will be minimum. So minimum will be there at where the diameter is more. So stress will be minimum where the diameter is more. So you calculate the stress, or if you don't understand, you simply calculate the compressive stress at D2. So put the formula here. Stress is equal to P by A. So P is the load applied and area is there. So 23 megapascal. Similarly, calculate the stress at D1. Area you calculated, P is given, area you calculated now, just put that and you will get 95.5 megapascal. So now we observe these two values. So from these two values I can say this is minimum. So you write sigma minimum. So sigma minimum is where it is occurring at D2. So D2 is 20 mm, higher value. And this 95 is higher value, so stress will be maximum here. So this is typing mistake is there. So this is sigma max because 95.5 is greater than 23. So this is the maximum compressive stress, and this will occur at D1 where diameter is smaller than D2, 20 mm. So here you make a correction. This is sigma max. Of these two stresses, this is maximum, right? So this is sigma max and this is sigma minimum, and you can observe that sigma max will occur at smaller diameter D1 10 mm, and sigma minimum, it is compressive stress will be minimum at cross section where diameter is maximum or where area is higher. So after you calculate the stresses at two cross sections, then you can calculate the length of the bar. So length of this tapering bar, the formula is this one. You just remember this formula, PL by AE. So it is area is nothing but pi by 4 d square. So pi by 4 you write here. D of d square, since there are two diameters D1 and D2, you simply write D1 and D2. So if I put all the values given here, you will get the total decrease in length because it is a compressive load. So length will decrease. So it's negative here. Similarly, you can calculate, we have a tapering bar with rectangular cross section. So this cross section is rectangular. So unlike circular, this is circular cross section. Diameter will be given. If the cross section is rectangle, then you have to take the thickness and the breadth here, or the height. So in case of rectangular cross section, length will be there. This is the tapering bar, and you can see the cross sectional is rectangle on the right hand side and also on the left hand side, but the breadth B will be different at the two ends. So the breadth or the height, it is at the smaller end you take it as B, at the bigger end we take it as capital B, and this T is the thickness of that rectangle. So this is thickness of the rectangle, and this is the height or breadth of the rectangle. So at this left hand side the cross section, the breadth is small b. On the right hand side the cross section, the breadth is capital B. So the load applied is tensile load here again, just like in the previous tapering bar, the load applied is tensile here, load applied is tensile, and we do the same analysis just like what we did for this derivation. We do the same derivation for this bar also. Only the change is the cross section. So here the cross section is rectangle. So area will be, formula will be changing, that's all. But the analysis is same. So we take a small element at a distance of x, and let the breadth be bx. So in the previous case it was d. We have taken the diameter d. In this case you take it as breadth as b or bx. So small b is for smaller breadth and capital B is for bigger breadth. So at x, the element, it is having a breadth of bx, and the length of this element you take it as dx here. So this is the length of this element dx. So now you analyze the same in the same way as previous one. So the breadth, that is height of this element at x is bx. So bx will be higher. So bx will be more than this b. So it is b plus the difference of the breadth over length L into x. It is same as this previous d2 minus d1 by L. So in this case it is breadth b minus b by L into x, and you take b by L as k, and you calculate the area. So area of this rectangle now. So what is the area of this rectangle? So area of the rectangle will be length into breadth, or breadth into thickness. So this is the area. Area of the rectangle will be this edge into this edge. This is thickness, this is the breadth. So at x it will be area will be bx into t. So area of this, the cross-sectional area of this rectangle will be bx into thickness t, and bx is nothing but, just now we did this, it is this one, b plus kx. So substitute that, and then you calculate the stress at x. So stress is nothing but p by a. So p is, keep it as it is, the load is there, and area just now we have taken this, substitute this term here, and now you go to the formula for change in length. So what is the change in length or elongation? Is nothing but PL by AE. So that formula PL by AE you substitute for this element. So P by A is nothing but this stress here, and length of this element is dx. So length of the element is dx, and E keep it as it is. It's a material property. So the change in length is nothing but PL by AE, or sigma length into E. Length is this element dx. Now we integrate the length over the length, total length, that is L. So this is the small length of the element dx, and if I integrate the change in length over the total length of this bar L, then I will get the total change in length of this bar. So now we calculate only the change in length of this element of length dx. If you integrate that, I will get the total change in length of the bar over length L. So same thing you do, you take this term, this is the change in length of the element, you integrate this element from 0 to L, we will get the total length, change in length for length L, and substituting all the values and integrating, we will get, so integration, all of you know, you are done in your mathematics. So the same you apply now with respect to dx, integrate with respect to dx. So E and T are constant, load is also constant, K is also constant. You take it out and integrate with respect to B. So integrate B with respect to x, with x, yes, and integrate it over 0 to L. So if you do that type of your mathematics, what you will get? You will get this formula here. So this is the formula for change in length of a tapering bar with rectangular cross section of thickness T and breadth varying from small b to capital B. You have to remember this formula. So in this formula, P, L and E constant. PL by AE, it will be same. Area will be changing, that's all. So for area, you should put this term here. So this is the change in length of the tapering bar with rectangular cross section. And similarly, this is the change in length of the tapering bar with circular cross section. So in the problem, if they give circular cross section, you use this formula. In the problem, if they give rectangular cross section tapering bar, you have to use this formula. So remember this formula here, and accordingly you solve the problems. So here one simple problem is there, direct problem is given, wherein you have a aluminium flat of thickness 8 mm and axial length is given 500 mm, and it is tapering bar with the width tapering from 15 mm to 25 mm. So it's a tapering flat, and the load is given, compressive load is given. You have to calculate the compressive load when the change in length is given here. So in this problem, the delta L is already given, so you have to calculate the compressive force. In the previous problem, change in length you have to calculate, and the load was given. So in this problem, the load is not given, you have to calculate the load, but the change in length is already given here. And Young's modulus is given, 67 GPa for aluminium. So just take the formula directly, substitute the values. Young's modulus thickness is given, small b is given, capital B is given, delta L is given, and this formula remains. You have to take this formula here, this formula, and you have to calculate P. Delta L is given here. So calculate P, you get in newtons. So here we have one more case where you have to calculate the elongation in a bar because of the self weight. So in the previous cases, we have not taken the weight of these bars. We have not considered the weight of the bars. So in some cases, when the bars are vertically fixed and the load is applied on them, so what happens is the load or weight of the self weight of that material will be, that extra load will be acting on this, apart from the external load what we apply. So here in this bar, we are not applying any external load, but the load is nothing but here the self weight of this bar. That's why we call this as elongation, because or due to self weight of the bar. So in this bar, we are not applying any external forces. We calculate only the elongation because of the self weight of the bar. So self weight itself is the force, tensile force acting on this. So here the force is nothing but the weight of this bar. So here, if you want to take the weight, consider the weight. So all the materials, metal property, density is there. So density is the metal property, and that metal property, it is rho here. So rho is the weight density of the material. So all the metals will have different weight densities, and the formula for density, it is mass by volume, and the formula for weight density is weight by volume. So volume of the metal is, because length of this bar is known, and the cross section area of this bar is known, area A. So A into cross section area into length will give the volume of this material. So volume, that is A into L and into weight density, will give the weight of the bar. So weight of the bar is nothing but weight density into volume of the bar. Okay, so weight density is nothing but weight by volume. So if you want, I want the weight now. So weight is equal to weight density, that is constant rho into volume of this bar, A into L. So but here again we have to calculate the weight over the length of this bar. So again we analyze this element just like in the previous cases. We take the element, small element in the bar, and we calculate the stress in this, and we go for the elongation formula directly. So here again you take element. So this bar is circular cross section. So you can see here the cross section is circular, and you take the cross section at y, the distance of y from bottom here, and the length of this element is dy. Instead of dx, we are taking dy, that's all, because we are taking it vertically. So conventionally vertical is dy, horizontal is dx. So instead of dx, we are taking dy, that's all. So you take an element. So this is the element at a distance of y from the bottom, and the length of this element is dy. So again you apply the same thing here. So weight of the bar weight of this portion. So weight of this element is nothing but density of the element into volume of this element. So volume of this element is nothing but area, that is A into length of this element is dy. So this is the volume of the element, small element, what you have considered here. So this is the weight of the element which at a distance of y with length dy. So weight of the element, this element is density, weight density into volume of this element. So volume of this element will be cross-sectional area A into length of this element dy. So then you calculate the stress as usual. You calculate the stress here. So stress is again load by area. So load is nothing but here the weight. So weight is given here. Weight into weight by area. So it is rho by A. So what will happen? You will get only rho into y. Similarly, strain is nothing but this stress by Young's modulus. So stress is this one by Young's modulus. So change in length is nothing but PL by AE. The same formula used. P is nothing but here the weight of the element here. So it is Py by E. So this is the change in length into dy. That is the change in length. So it is strain is nothing but it is d, that is change in length by original length. So change in length is nothing but the change in length. Change in length is nothing but the strain into original length. So this is the original length and this is the strain. So this into original length, that is y dy, that is length of the element, is the change in length. So that is the formula. So here in this case you are taking the load as in terms of weight density into volume, right? And you are calculating strain. So strain is nothing but stress by Young's modulus. And change in length is nothing but it is related to strain. So strain is again change in length by original length. So change in length will be strain into original length. So strain into, that is P rho y by E into length is dy here. So now we take the change in length over the length L. So integrate that and you will get this formula. So here it is density. So instead of you can see here density, weight is nothing but weight density into area into length. So it is the weight density into volume will give the weight. So you can apply that and you will get this formula here. So rho AL is nothing but weight. So you will get WL by 2AE. So instead of P, the load applied. So here in this case there is no external applied load P. So whatever load is there, it is because of the self weight, that is W of that bar. So self weight PL by AE. So it is same, the formula is same. Elongation of this bar will be PL by AE. But here 2 you have to add here. So it is half of this formula, and instead of P it is weight of this element. So weight of this bar, if it is density is given, you multiply the density into volume of this bar. So cross section will be given, length will be given, you calculate that weight of the bar, that is P, load acting on the bar. The length PL by AE as it is there, so that these two you have to add here. So it is very easy to remember this formula. So it is same as PL by AE, except that 2 is already in the denominator, and the P of external load you have to consider the weight of this bar, and weight of this bar is related to density rho of this bar and area, cross-sectional area of this bar into length, that is volume. So A into L is volume of this bar. So if the cross section is circular, A will be pi by 4 d square. If the cross section is rectangular, then it will be length into breadth or thickness into breadth. So accordingly we calculate the area and get the answers here. And you can see here in this diagram how that stress varies in this bar. So at the bottom here the stress will be 0 because area will be 0 here, and as you go as you go along this x, okay, as the weight increases, so here the load will be 0 because of the self weight, the load will be 0 here. As you go above, the weight of this bar will be increasing. So the weight will be considered here and the stress goes on increasing. So you can see the stresses at different cross sections, it goes on increasing. Right? So as because load increases, the weight increases along this cross sections. So at different cross sections, the stress goes on increasing. So this is how we represent the stress. So stress in the bar gradually increases from 0 at bottom to rho into L at here. So rho into L is nothing but because of this is the stress, rho into Y. L is the full length of the bar. Rho is the weight density. So the stress in the bar will be 0 here, and as you take cross sections at different lengths towards the top, the stress will be increasing. So this is the magnitude of stress. You can see the stress is increasing from 0 to rho into L. So based on this, we have one problem here. So here we have the suspended bar. So the load is no external load is applied, but we have to consider the weight of this bar. And this bar is a stepped bar, so it's not a straight bar; it's a stepped bar. So we have two different cross sections. So we should again take these portions, that is A, B, C. So you take this as portion AB, this is portion BC, and accordingly you find out the stresses in the bar. So in this problem you have to find out the stresses in the sections B and A, that is in this portion and in this portion, because of the self weight. And here you can see the weight density is given, rho is given, Newton per millimeter cube. So load by volume, that is given here. And you have to calculate the stresses, so as well as the change in length of this bar. So here the load is nothing but the self weight of the bar. So just now we derived the equation, so that equation we will be using here directly, and we will calculate the stresses and the total elongation. So first we will calculate the stress at bar B due to weight of the portion BC. So we will calculate the stress in this portion, that is second portion. So this is B, portion B. And here to calculate stress, I require the load as well as the area. So first we calculate the area of this portion. So what is the cross section is circular, diameter is given 6 mm. So you calculate the area pi by 4 d square. Then you calculate the weight of this portion BC. So weight of this portion is nothing but it is weight density of the material into area, cross-sectional area of this material, of this bar, and length of this bar. So length is given here 1. So weight density is given, it's a metal property, it's given here. And area, this area you have to calculate, cross-sectional area is circular, so it is pi by 4 d square, you calculate that, you substitute here. Length is given 1 meter, take it in millimeter, and you will get the weight in 20 as in newtons. So once you know the weight, so what is stress? Stress is nothing but P by A. Stress is nothing but P by A. So in this case, P means the load or the self weight of the bar. So the weight by A or P by A. Substitute that, you will get the stress in this portion B. It is 0.76 megapascal or Newton per millimeter square. Then similarly, you have to calculate stress at A. So in this portion, the weight will be because of this plus and this. The weight of this portion will be this plus this. So you can see here the stresses at A will be due to load acting on this as well as on this. So at this point there will be weight acting for this portion, weight of this portion and weight of this portion. So at this point the total weight will be acting. So here you have to consider the weight of both the portions, that is P divided by area 1. So this cross section area, that will give the stress in this portion. So the load acting on in this portion will be because of this portion as well as this portion. So you have to add the weight of these two portions. So W1 and W2. W2 is this portion, already you have calculated that. W1, so what is W1? The weight of this portion will be weight density into the cross-sectional area of this portion into length of this portion, that is W2. So length is given 1 meter here. Again area 1 is nothing but the same formula, it is circular here, 10 mm diameter. You calculate the area 1 and substitute that, you will get the weight of this portion as 60 Newton. So weight of this portion is 21 Newton, weight of this upper portion is 60 Newton. So the total load or the weight acting on this portion will be W1 plus W2, because this portion carries this load also. So the total weight acting will be at this point because of this weight and this weight. So if you want to calculate the stress in the upper portion, you should take the load of these two or the weight of these two portions. And area will be this area only, area of this first portion. So that is, if you do that, you will get the stress 1 megapascal, a Newton per or 1 Newton per meter square. Then you can go to change in length. So again we will calculate the change in length of this portion and change in length of this portion. So here change in length of this portion, the load acting on this portion is only how much? W2, and the formula just now we derived. So you apply this formula here. Change in length is WL by 2AE. So change in length BC will be W2 L2 by A2 and E. E is common because it is a metal property. For both portion E will be there. So 2AE, right? W2 is nothing but the weight of this portion. You calculate that 21. Length of this portion is given 1000 millimeter. 2 as it is. Then area of this portion, the cross-sectional area pi by 4 d square, diameter is 6 mm. You calculated that, and Young's modulus is given 200 kilonewton per millimeter square. You substitute that 200,000 kilo is 1000, 200,000 Newton per millimeter square. So keep all the units in millimeter square only. You will get the change in length in millimeter. Similarly, calculate the change in length in portion AB. So change in length in portion AB is again, you have to calculate the change in length because of this weight and because of this weight. So you have to calculate the change in length of these two. That will be the change in length of portion AB. So it is because of this weight and because of this weight, the change in length will be there. So you take change in length for portion AB is equal to change in length due to weight of this AB as well as the weight of this portion BC. So you have to add both the change in lengths. So the same formula you add for both the portions, and you can substitute that, you will get this value. So now the total change in length will be change in length of this portion plus change in length of this portion. So you add those two, you will get the total change in length. So this bar elongates by 0.005 millimeter, or you can take it as, okay, anyway, it's in millimeters only, 0.005 millimeters. So very small elongation will be there because of the weight of this bar. So it's negligible. You can see here it is very small value. Its weight of the elongation because of the weight is negligible here. You can see here. So this is important in portion AB. Whenever you are calculating the portion, the stress in AB, first stress in this portion, we will take the load of both the portions here, and when you are calculating the elongation in this portion, we should calculate the elongation of both the portions here. So that is the elongation of this portion, and then you add these two elongations of these two portions, you will get the total elongation. Okay, that's it for this session. We will continue with the next session later. Thank you.